sigma notation is basically the S, the sum. It's a Greek letter. And this is S, but it's a Greek letter. Okay, the sigma. Sigma is the sum. Okay? And this notation was preferred. Why don't we use this? What's wrong with this? Well, this is a much better design for what we need, but this is the same thing. Okay? So the sum of, let's say, 2i from I equals 1 to 4. What does this mean? So you can put parentheses if you like or not, it's still the same thing. So this is basically the following. When I is 1, I have 2 times 1, which is 2. The sum says plus. When I is 2, I have 2 times 2, which is 4. The sum says plus. When I is 3, I have 2 times 3, which is 6. The sum says plus, and I have to end with 4. When I is 4. When I is 4, I have 8. So this is called the index. This number is the lower. I don't want to use the word limit in the sense of a limit. I will use it as the lower limit of sigma notation. This is not the limit that we know from this class. It's just the limit of the sigma notation, the lower limit. And what is the upper limit? 4. Upper limit of the sigma notation, or if you want, upper limit of the index from I equals 1 through 4. And this is sum. So this is 10 and this is another 10, so the answer is 20. Now, what if I have something like 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed? I'm going backwards. So I'm given this. Can I come up with that? Yes. It's the sum.
So then will we put the equation that all of them, so replace 1, 2, 3, 4, and 5 with I?
With the sigma, exactly. So from I equals 1, indeed, from 1 to 5, 5 is the maximum, or the upper limit of the index. And this is I to the third, I to the third, I to the third, I to the third, I to the third. That's it. We're not going to do a lot with this. In my STEM class, I do a lot with this. Okay, but you're going to see why this is important. Okay, now, let's suppose I want to find or estimate, if I cannot find exactly, the area under a very simple function, x squared, on the interval 0, 2. So before we discussed any of this, I just wanted you to at least get the idea of the sigma or summation notation, how it works. It has properties. There are 3 properties. We're not going to need to do that, but at least you have the idea of what the summation notation looks like. You'll see why we need that. So I want, for some reason, I want to find or estimate, if I cannot find exactly, at least an estimate of the area under the graph of x squared on this simple interval 0 to 2. Well, I have to graph it first and see what's happening here. Okay. 1, 2, 3, 4. 1, 2. At 0 is 0. Again, where I'm graphing f of x equals x squared on the interval 1, 2, 0, 2. At 1 is 1. At 2, 2 squared is 4. So here's the graph. of x squared only on the interval 0, 2. Okay. Let's say we want to estimate first, number 1, using 2 subintervals and leftmost point. Number 2, the same 2, but using the rightmost point. And number 3, I like to use 4 subintervals, 8 subintervals, 16 subintervals, and so on and so forth. Okay, so let's see what happens. So if I have 2 subintervals and the length of the entire interval is 2, the width of each subinterval, of course, is our favorite delta x by now, and that is the length 2 minus 0 divided by 2 subintervals. The general formula for any interval a comma b and n subintervals will be, of course, delta x equals b minus a over n. 2, so our interval was 0, 2, and we had n equals 2. 2 minus 0 divided by the number of subintervals. If I have the interval a comma b and I have n subintervals, b minus a over n is the width of each subinterval. Okay, so in this case, this is 1. Okay, fine. I'm coming back to the graph. And then I just need a different color here. Okay, so what does the leftmost and what does the rightmost point mean? Okay, the leftmost point, so I have 2 subintervals, this and this. And I have to use rectangles. So at this point, the height of the rectangle is 0. The base is 0.5. I'm sorry, the base is 1, but the height is 0. So this first rectangle has area 0 because there is no height. Well, let's move on to the next one. Using the leftmost point, it means that this will be the height. This is the interval. The leftmost point is here. So where the vertical touches or crosses the function, this is my rectangle. So the area left with 2 subintervals is approximately base, which is 1, times height for all of them, right? Base times height, base times height. So 1 times f of 0 plus 1 times f of 1. One more time. 1 times f of 0 plus 1 times f of 1. So this is 0. F of 1 is 1. So this is 1. 0 plus 1 times 1. How will it look like? How will it look like with the rightmost point? Let's take a look. Imagine that I'm graphing this same function again. So this is 0, this is 1, and this is 2. Here's what happens next with the rightmost point. Base times height base times height, the rightmost point. Question here. Actually, the area is this, right? Of course, this should be till this point. So this is the entire area. But I only have this area, which is 0, and this area, which is 0, which is 1 times 1. So my question is this an overestimation or an underestimation of the exact area? What do you think?
Be an underestimation.
Of course, because I'm missing this piece and I'm missing this piece. Thank you very much. Underestimation. Good. Of the exact area. Now, will anyone tell us whether this is an underestimation or an overestimation using the rightmost point for this function? For other functions, it may be the other way around. But for this function that I picked x squared. If I use the rightmost point, so the area with the right 2 will be approximately still base times height, which is 1, times height, which is f of 1, plus base, which is 1 times height, f of 2. So this will be f of 1 is 1, f of 2 is 4, and this is 5. So is this an underestimation or an overestimation of the exact area?
Overestimation.
Of course, this area is not under. Grossly overestimate. Overestimate. Okay, perfect. So now bear with me, because I have a question for you. Let's say I have 4 subintervals. So I'm going to have this height with the rightmost point, and then this height, and then this height. Let's say now I have 16. I don't know if I can show 16, but we'll see. Sorry about that. I'm still discussing the rightmost point. So which of these two, this one with 4, n, number of subintervals is 4, and here n equals 2, 4, 6, 8. I only showed 8. Which of these two will be a better approximation? With 4 or 16 with the rightmost point? Yes, we know they're overestimations. For this function increasing like that, the rightmost point will be always an overestimate. So, but which one will be a better approximation of the exact area? This one or this one?
N equals 8.
Of course, this will be better. What if I use now 16 or a later 32 or 64 and so on and so forth? Which one would be the best? And what concept am I talking about? As n approaches infinity. What concept is this? What do I have to write above?
Limit.
Thank you very much. Limit of what? Excellent. Limit of what? Base times height plus base times height plus base times height plus base times height. Base times height plus base times height plus base times height plus base times height. From the first subinterval to the last one, from base times height. F of xi, because I depends on the location. If I'm talking about the first subinterval, then the height will be this. If I'm talking about the 7th or the 6th, then the height is this. If I'm talking about the 7th, then the height is this. So this depends on I. Depends on which rectangle I'm working on. But that's the sigma notation, and that's why I wanted you to understand that this is basically a condensed way of presenting a sum. I cannot even write, this is n. I would have to write it indefinitely. Delta x times f of x1 plus delta x times f of x2 plus delta, no. We are writing it condensed using the summation notation. So this will be the exact area. Nothing is missing. No overestimation, no underestimation. As long as I calculate the sum of base times height plus base times height plus base times height from the first rectangle till the last rectangle, and this last, or the n, approaches infinity, there is no approximation here. Everything is taken care of. And this has a name. It bears the name of the person who invented it. His name is Riemann. It's the Riemann sum. Okay, I just would like to illustrate with one example, and then we'll move on. Okay, I found an example.